Down? Yeah. We're good? All right, excellent. All right, so this is joint work with Dan Licata and Ramya, and it also follows up on work that I did with Jim Royer earlier and Jennifer Pakin. So sort of the big picture here of what we're working towards is trying to develop some techniques for translating, say, programs in a source code language into a new language, into another language that basically gives us recurrences to describe the cost of evaluating the programs. All right, so that's sort of the big picture of this. So in this particular paper, we're working with a source language that's basically a variant of System T, inductive data types, higher order. And so something that's not going to show up in the slides but is in the paper, we also allow function type arguments for in the inductive data type constructors. It complicates a lot of definitions, so they're not showing up here. But you have things like map in there. You see in the formal language the recursor construct that describes the map function, but really just think of the ordinary equational definition. And then we have a big step evaluation semantics annotated with costs. And so, for example, function application, we charge a unit cost for the function application, so total costs, right? You have to evaluate the operand and the operator, as well as plugging in the operand into the body. So we charge for all that and one more. We charge for recursive calls, and in this paper we don't charge for anything else, but the overall structure lets you charge whatever you want for the various kinds of steps. So that's the source language. And now, when we're talking about trying to develop recurrences for describing the cost of evaluation, really we can't quite get away with just translating into recurrences for costs alone. At some level, this really just has to do with compositionality. If you're going to start translating and developing recurrences, in some sense, we want to be able to compose the recurrences themselves to extract information about the cost of composing functions in the source language. Right? And so we also need to know information then essentially about the sizes at the same time. Right? So as you compose, right, if you know about the if our costs, our recurrences are telling us about the costs in terms of the sizes of the arguments, then as we compose, we're also going to need those same recurrences to tell us about the sizes of the results so that we can then use those in other recurrences. So that then leads to one question, if we're dealing with a higher order language, as to what do we mean then by the size of a function or any sort of higher order value. And so in some sense, I think maybe the right way to think about this is that when we think about talking about costs and complexities, what's relevant about size when we think about sort of base type values, what's relevant about size is that it's really giving you information about how those values contribute to the cost of computing with them. They're essentially telling you some sort of use cost information as opposed to just the cost of evaluating those expressions themselves. And that gives us an idea of what to do with functions as well. It's basically still going to be use costs is the notion of size for functions. And so the use cost of a function is basically essentially just another function itself, and it's a function from sizes, which we think of as the sizes of the values to which that function is going to be applied, back to complexities again, right? So cost of evaluating that function on an argument of that size along with the size of the result. So all of these recurrences that we end up developing give us complexities, which are pairs consisting of a cost and a size in some sense, size suitably interpreted. So the second issue is that if we have arbitrary inductive data types, then we have to ask ourselves about what is, say, the size of a tree, right? And so that's going to be my running example through this entire talk is the data type of NAT-labeled trees. But you then have to ask, okay, what about the size of the tree? And of course, there are many options. And from our perspective, we don't want to impose a definition of size for the inductive data types, right? We really feel this is something where, say, this is a system where a user should basically be able to decide this is what is relevant. This is the relevant notion of size for the kinds of analyses that I want to perform. So that's something that's going to be left up to more or less the programmer, the user of this system. And we're just going to simply place a few constraints that have to be followed for everything to carry through. All right, so with that in mind, then, what is this complexity language? The complexity language, which is where the recurrences are expressed, are more or less the source code programs now paired up with evaluation cost. It's the semantics of the language that's really going to give us sort of the kinds of recurrences describing complexity that we think about, that we might be thinking about. And so this translation is ultimately, in some sense, basically a monadic translation into the writer monad. But we're going to sort of look at it as just written out explicitly here. So for example, how about the translation of application, function application? Well, so there's two components again. The translation always gives two components, a cost component, which is first, and a size or potential component, which is second. And so the cost of application, well, we charge one for the application itself. We have the cost of evaluating the operator, the cost of evaluating the operand. And then there's that last part about plugging the value of the operand into the body of the operator. And so how do we get the cost for that? Well, keep in mind that, in fact, that's exactly the kind of information we get out of the use cost of the operator, right? So the potential of the operator tells us the complexity, i.e. the cost and the size of applying the original source code function to a value of a given size. And so we look at the potential of the operator and apply that to the potential of the operand, right? What we get back is a complexity. It tells us the cost of that plugging in, right, which is what we take and we add that into the cost component here, as well as the potential of the result. And since the result of the application is just the result of that plugging in, we can take the potential of the result to be the potential of the application of the potentials there. All right, so that's the sort of idea behind this translation. Data type constructors pretty much get translated as themselves, right? So the complexity language parallels the source code language in terms of having sort of the same constructors, but now the arguments to the constructors range are, instead of now take not complexities, but just potentials. Think sizes here. All right, and so it's really going to be the semantics of those constructors that really plays the role in how we use that information. And then recursive definitions in the source language are then just translated more or less just to recurrences in the complexity language. But now the recurrence argument is the potential, the size of the original recursion argument from the source language. All right, so applying this then, thinking back to map, what happens, say, if we translate the map function under this, then what we get here, taking a look at that second line, so keep in mind now what happens is that when we're looking at the translation of map, right, the argument f to the translation is really standing in for the use cost of the argument to the source code map, the function argument to the source code map. Right? And the second argument is standing in, obviously, for the tree being mapped over. And so what is the recurrence that we end up getting? Well, we really, of course, get two recurrences, one for cost, one for size, or one for potential. And the cost recurrence is then 1 plus the cost of applying the function to the label of that node, right? And so again, we're keep in mind that f in the complexity language is really the use cost of the original one. So we're doing that same basic game as we saw with the translation, along with recursively computing the costs of applying mapping over the subtrees. And then the potential is basically just building up that node structure again. And so once again, it's going to be the semantics of the constructors and the recursion construct in the complexity language that really count as far as trying to understand what we get here in terms of bounds and so forth. And so one possible semantics then is essentially a size-based semantics, and this is intended to be a semantics of the complexity language that is going to try to capture sort of our what we'd consider, I guess, usual notions of sizes for ordinary inductive data types that would correspond more or less to the kinds of algorithm analysis you might teach in an undergraduate algorithms course. Right? And so now we interpret inductive types from the complexity language, which are mirroring the inductive types in the source code language. We interpret those as just some sort of partial order. And we can extend that order point-wise, component-wise through the rest of the type hierarchy. And so, for example, for the one that I care about, if we, say, happen to be analyzing the map function, a fairly reasonable notion of size for trees in this case should take into account both, say, the number of nodes in the tree as well as the size of the labels of the tree. Because if we're going to map some function over a tree, right, well, we need to know the size of the tree to know how many times we're applying the function. But applying the function itself to any of the labels also has a cost to it, right? And so knowing something about the sizes of those labels is also going to be important. So we might take pairs of numbers representing sort of numbers of nodes and maximum label size as being an appropriate notion of size of a tree here. And now we have to define some notion of a size function. And so if the data types are interpreted as just some partial order, it's a little bit tricky to define a size function in a reasonable way, because we sort of want to say, well, we're talking about sizes of the empty tree and sizes of nodes built up from things. And if all we have is, say, natural numbers, those don't quite mesh up. And so basically we do something a little bit like views. We can sort of split things up a little bit in such a way in the semantics so that we can define a notion of size And sort of the right way to think about this here is that when we're looking at the size of, say, a node, right, what we're really talking about there, when we talk about the size of a node of A, B0, and B1, that's really talking about the size of some sort of a node whose label has size at most A, and whose left subtree has size at most B0, and whose right subtree has size at most B1. Right, so that's sort of the right way to understand what's going on with these size functions. And then there's basically the one constraint that we have is that when you are looking at, when you're defining these size functions, you can do pretty much anything you want, except that when you're looking at the size of a built-up structure like a node, right, that size should be strictly larger than the size of the substructures of the same type, right? So if I'm talking about the size of a node of things where the right subtree has size at most B1, the size of such a thing should be strictly bigger than B1. Right, and that seems like a fairly mild constraint on notions of sizes in this case. All right, so given that, then we can define, say, the semantics of the data type constructors from the complexity language, which basically just simply pass through this size function, right? And so now the semantics of a node is really the size of the node of the interpretations of the arguments, right? And so so those sizes, the interpretations still come out in those original partial orders. And then what's the interpretation of the recursor, or the recurrence operator in the complexity language, right? Now it's basically just a maximum over all of the possible smaller things that you might have. All right, so that recurrence, that big maximum is a potentially very large maximum, and it does look a bit ugly, but in fact, in sort of all of the ordinary cases, it disappears very quickly. And one of the things we'd actually like to understand is how to get rid of it in a more principled way, as opposed to sort of an ad hoc analysis each time it comes up to eliminate it. But it goes away, and then, for example, if you go back to the translation for map, and look at the recurrence that's generated and then apply this particular semantics, you end up with pretty much exactly the right recurrence and the right solutions to that recurrence, which tell you that the cost of applying function f over a tree with at most m nodes whose label size is at most s is what is shown down there, which is pretty much what you would expect. All right, so that works out well in this one example. Of course, we'd like to know that it always works. And so for that, right, we go back to the syntax and basically ask, okay, sort of what was involved in trying to make that ensure that that particular bound that we got was in fact the correct bound for that semantics. We pull it back to the complexity language, sort of look a little bit, what do we need out of the ordering? And we need relatively little. But basically pull that order back and basically impose a pre-order in the complexity language at every type. And basically, what does that pre-order says? It more or less says that the readx's are greater than or equal to the contractums, right? It's closure under head expansion, more or less, because we're going to have now a logical relation between source language programs, little e, and complexity programs, big E. And that relation tells us that if the source program evaluates at cost n to some value v, well, then on the one hand, n is in fact bounded by the cost component of that complexity expression, and the value is then value bounded by the potential component, right, which is really where the interesting stuff comes in. And in most cases, that value bounding relation basically just dives right inside, right? So when is a node value bounded by an expression? Well, provided we can value bound all the components in sort of the obvious way there. All right, the logical relations come up when we start talking about function values, right? So when is a function value bounded by an expression? Well, provided that whenever we have bounds on the arguments, which in this case would be value bounds since it's a call by value language, right? So whenever we have value bounds on arguments, when we plug in on the left in the source language, we get a bound now, not a value bound, but a regular bound on the right-hand side, right? And so that pushes all the way down through the type structure. So the main theorem then is that for every closed source language program, it is bounded by its own translation. Right, and so that really tells us then, if you sort of parse through the definition of that logical relation, right, it tells us that if the program then evaluates at cost n, then in fact n is bounded by the cost component of that translation. And then the potential is also value bounded. So it's reasonable to think at first pass, oh, it's the first part that's interesting, right? We've got this bound on the cost, and that's sort of what we're always after, right? We want to say that we've got the right bound on the cost of evaluating the program. In fact, it's actually the second part that's really the interesting part here, right? Because normally these source language programs, right, they are functions. They're values already, right? So the cost of evaluating them, constant, uninteresting. Is the second part of that value bounding relation. What it tells us is that that potential of that translation, that's basically a recurrence. Right? And so this theorem is now telling us that that recurrence, in fact, is a correct description or a correct bound on the evaluation cost of applying that particular program. All right? So that's really what the important part of this theorem is. And so now, right, given this more syntactic bounding theorem, right, that just works with, that basically is just talking about relation between the source language and complexity language programs, right? Now, if you follow that up with, say, any particular semantics for the complexity language, you can try to push that through and see what kinds of information you get about bounds. And so if you take that size-based semantics, so it is hopefully not a surprise that we designed the size-based semantics and ensured that it was, in fact, a model of the complexity language. When you push that through, what you get is sort of your ordinary, everyday upper bounds on costs in terms of size of the arguments, right? So if you do this all with lists, right, you can sort of write down, say, insertion, sorter, whatever sorting algorithms you can write in this, and you'll get sort of your standard costs, execution costs in terms of lengths of lists. Right, and you can do, say, membership tests on trees, and if you want your size of a tree just to be number of nodes, right, then you can do the same sort of thing. Right, you can take, admittedly it's a little bit of a hokey model, but you can do this, right? You can take the term model of the complexity semantics. That also is a model of the complexity language, and what you get then is that the costs are the exact costs of computation, right? So you get the exact costs of evaluation of the original source language program. Which sounds all well and fine, except for that then you discover to reason about that in any way. You then have to know everything there is to know about actual execution, what values are actually coming up in that source language. Right? And so then hopefully we start talking about other kinds of semantics to continue this onward. All right, so there is plenty more work to be done in this area. And so there are some of the ideas up there, but I think I will stop here and take questions. Thank you. All right. Yes. Yeah, so general recursion is to me at least sort of the most important next step, right? So right now this system, it's system T, it's structural recursion only. So you can program a few things in that, but it would be a lot nicer to have general recursion and understand how to work with that properly and push that through. And then the solution techniques, these recurrences are a little bit higher order-ish, especially if we're talking about higher order programs. So understanding how to solve these things would be really nice to know.
Sorry. I had a question. Yeah. So when you have some kind of cost model for the subdata, like for the trees, you had the maximum of the costs of the of the values. Is there some sort of richer structure that you can encode in there besides taking some sort of maximum or average, I guess?
Yeah, I'm not sure yet whether we really can. This is something that we'd like to understand this a little bit better, right? So that big maximum that shows up in the interpretation of the recurrence operator really shows up because we're allowing sort of arbitrary inductive data types, and you can do all sorts of dumb stuff that we have to account for. But if you don't do that dumb stuff, that big maximum just goes away. And you get sort of the recurrences you would expect to get just by looking one level lower, pretty much. And so we'd actually like to understand sort of how to formalize not doing dumb stuff to simplify that.
Thanks.
So does this generalize to lazy languages?
Say again?
To lazy languages?
That is on the list to understand, yeah. Thank you.